2.5 weeks ago, just before Christmas break, we defined a new term, radioactivity. We said it was a natural process, a random process, whereby one nucleus decays into something else. By a natural process, we mean a process that we don't make happen. We don't force it to happen. It's going to happen on its own. By random means, it's going to happen when it wants to happen. If it wants to happen, it's going to happen. If it doesn't, it's not going to happen. If it wants to happen, it's going to happen when it wants to happen. We have no control over it whatsoever. It's going to do what it's going to do, and it's going to do it when it wants to do it. Now, when this nucleus decays into something else, what results is what we call ionizing radiation. Ionizing radiation is radiation that can ionize atoms, turn atoms, neutral atoms, into ions, charged atoms, basically. Okay, and what's the big deal with that? Well, ions can react in ways that atoms can't. So that means that if you have ionizing radiation inside your body, okay, then it can cause chemical reactions that aren't supposed to happen inside your body and lead to all kinds of problems, like just sickness, radiation poisoning. It can lead to cataracts, okay, in your eyes. It can lead to certain types of cancers. Okay, it can lead to all kinds of different issues caused by chemical reactions inside your body that aren't supposed to happen. Now, just before the break, we talked about these three types of ionizing radiation: alpha decay, beta decay, and gamma decay. There are two things that come about when radioactivity happens. Okay, you got this big nucleus. Well, it's not always a huge nucleus, but this nucleus, we'll call it nucleus A, that decays, and it produces a new nucleus, B, which isn't much different, but is a little bit different than A. But it also produces this other little thing right here, C. This little thing, C, is your alpha, beta, or gamma. So if you've got uranium-235, maybe you produce thorium-231, and then a little alpha particle. This is the one that we're concerned about right now, this tiny little particle, not the big nucleus that remains, the one that's slightly different than the original, but almost the same. We're concerned about this tiny little particle that's breaking off there, that particle C. That's the alpha particle, the beta particle, or the gamma ray. Now, an alpha particle is a notation that looks like this, 4,2 alpha, which means that it's got how many protons? How many? No. How many protons in an alpha particle? 2, right? Bottom number is the atomic number, the number of protons. 2 protons in an alpha particle. So that little particle C that's broken off consists of 2 protons and 2 neutrons. Now, an alpha particle is chemically identical to a helium nucleus. So sometimes you actually see it written as 4,2 He as opposed to 4,2 alpha. If you see it either way, it means exactly the same thing. So don't panic if you see it written one way or the other. Okay, you write it whichever way you want. But if you see it on an exam written either way, it means the same thing. Beta, well, there's actually 2 types of beta decay that we'll talk about. There's beta negative. Beta negative decay produces a particle, that particle C, that looks like this, 0 minus 1 beta, which consists of 0 protons, 0 neutrons, and 1, what is it? No protons, no neutrons, 1 electron. So sometimes you'll see a beta particle written like this, 0 minus 1 E, as opposed to 0 minus 1 beta. Exactly the same thing, though. Now, the other type of beta decay, beta plus or beta positive decay, 0 plus 1 B. 0 protons, although you look at that bottom number and think, oh, there's 1 proton. No, there's not. The top number is the number of protons and neutrons combined. There's none. There's no protons and neutrons combined. So there's no protons, there's no neutrons. What are we left with then? That plus 1 means the antiparticle of an electron. It's a positron. It's antimatter. Has all the same properties of an electron, all of them exactly the same, indistinguishable from an electron, except for the charge. It's positive instead of negative. Finally, gamma, 0, 0, gamma, no other symbol for that. It's just electromagnetic radiation. No protons, no neutrons, no electrons, no positrons, no nothing. Just energy. Just pure energy. Now, how are these produced? How do we make these little particle Cs, these tiny little particles that get broken off of the atom, of the bigger nucleus, these chunks of ionizing radiation? Well, alpha decay occurs in big nuclei, big ones. Like if you got a nucleus like carbon, which only has 6 protons and 6 or 7 or 8 neutrons, depending on the isotope, alpha decay will not happen. Okay, this happens in big nuclei like uranium or thorium or something big like that. And it happens when you get too many protons. But why? Because in that nucleus, where you have too many protons, any nucleus for that matter, you got 3 forces acting, 2 of which we really care about right now. There's the strong nuclear force. The strong nuclear force is attractive. And there's the electrostatic force. The electrostatic force can be attractive or repulsive, but in the nucleus, because you got protons and protons, it's a repulsive force. If the strong nuclear attractive force, which acts between protons and neutrons, neutrons and neutrons, and protons, if it's bigger than the repulsive force that acts just between the protons, then the nucleus will stay together. It's stable. But if the repulsive force is bigger, then the nucleus won't stay together. It breaks apart. Well, if you get too many protons, then the electrostatic force will be too big compared to the strong nuclear force. In other words, the repulsive force will be bigger than the attractive force, and the nucleus won't be stable. It's going to break apart. So if this guy wins right here, then the nucleus breaks apart, and off this alpha particle goes. Breaks off of the nucleus and flies off somewhere. Beta decay, beta negative at least decay, occurs when you got too many neutrons. This nucleus, this finicky nucleus that doesn't like to be stable. Remember what we said before Christmas? There's only like 10 or 20% of all nuclei that are actually stable. The vast, vast majority of nuclei, of isotopes, of the 20-some odd hundred isotopes that exist, the vast majority of them are not stable. The vast majority of them are radioactive. There's a reason for that. Because the nucleus is so finicky. You get too many protons, this happens. You get too many neutrons, this happens. You got to have this perfect balance of protons and neutrons in order to keep it stable. And that's hard. It's difficult to get that perfect balance. So, too many neutrons. What happens? Why is that a big deal? Well, if you get too many neutrons, it's just not energetically favorable. The energy of the nucleus isn't good. So it wants to become more favorable. We talked about the nucleus club before Christmas. You get too many neutrons, what do? You say, get together and say, well, let's get rid of a neutron. But we don't want to get rid of a neutron because we like neutrons. Neutrons are part of the club. So are protons part of the club. But we got too many of this part of the club. We get too many neutrons. So we don't want to kick a neutron out. Rather, what we want to do is change a neutron. We take a neutron and convert it to a proton. We get too many neutrons, not enough protons. Let's change one. Let's turn it into a proton. Perfect, right? Now we got less neutrons, more protons. Perfect. The balance is so much better now. The problem is right now this violates the law of conservation of charge. Neutral became positive, and that can't happen. Neutral has to stay neutral. So in addition to this proton what else is produced? An electron. And this electron, it's not part of the club. These guys in the club say, look, hey, we had a neutron. We like the neutron. We just had too many of them. Now we got a proton. Perfect. Like this guy, like this guy. It's all good. But the electron, we don't like him. Okay, electrons aren't part of the nucleus club, so he's got to get out. So he does. That's that little particle C again. That little chunk that's broken off and flown out of the nucleus. That's the beta particle. I got beta plus. Once again, in this case, we get too many protons. Energetically unfavorable again. So what do? Let's change a proton into a neutron. Perfect, right? You had too many protons, not enough neutrons. Now we got less protons, more neutrons. Perfect. But this violates the law of conservation of charge because positive can't become neutral. So in order to conserve charge, we've got to make something else here. Positive becomes neutral and positive. In other words, a proton changes into a neutron and a, what's that word? A positron. Or you could call it an anti-electron because it's the antiparticle of the electron. This guy was just changed. He was welcome in the nucleus, but he's changed because it was too many of them. This guy's welcome in the nucleus because it makes him more energetically favorable and neutrons are part of the club. For this guy, this positron, he has to leave just like the electron did in the other one. That's the positron, the beta plus particle that's been ejected. Gamma decay, that's a little bit easier. Gamma decay occurs as a result of above. What do I mean by that? Well, when something like beta decay occurs, the nucleus is left excited, but it doesn't want to be excited. It's like Eeyore. Something's happened. He's a little bit excited, but he doesn't want to be excited. He wants to be, oh, So he wants to go back down to its normal state. And it does. It goes back down to its normal unenergized state. But it's got to give off energy in that process, and the energy that it gives off in that process is this electromagnetic radiation, this gamma ray photon. Make sense? No matter, it's not matter, it's just energy, a photon of light. That's where we left up before the break. Now, there's a couple more little things that I want to tell you about alpha, beta, and gamma before we talk about the specifics of the reactions. Okay, two properties, the penetrating power and the ionizing power, or ionizing potential. Penetrating, can't spell that. And the ionizing potential. What does that mean? Well, the penetrating power means how easy it is or how difficult it is for this to penetrate matter. If you have a sharp knife, it will penetrate a piece of paper easily. It will go through a piece of paper easily. So the penetrating power of a sharp knife is pretty high. Okay, the penetrating power of a balled up piece of paper is not very high. You throw a balled up piece of paper at a big sheet of paper, it's not going to go through it. Okay, the penetrating power is its ability to go through matter. The ionizing potential is its ability to turn atoms into ions. In other words, to strip electrons from atoms or to put in extra electrons into atoms. To ionize atoms, to turn atoms into ions. The penetrating power of an alpha particle is very low. That's good news. It's very low. Like maybe a sheet or two of paper. Listen, we've been in this class now for 17 weeks, 18 weeks, whatever. Okay, there's 2 weeks left in class. You guys get upset. You guys have seen enough of me. You guys have had it. You guys want to come to school one day with your alpha particle gun and just do me in. Go ahead. Make my day. Bring your alpha particle gun. Okay, my shield for your alpha particle gun will be this piece of paper. You can't kill me with your alpha particle gun as long as I have a sheet or two of paper in front of me, because the penetrating power of alpha particles is so small that a sheet or two of paper is going to stop those particles. The penetrating power is very, very low. Gamma rays is very high. So don't bring your gamma gun in. Don't bring your gamma gun. Because gamma rays will penetrate matter to several centimeters of lead. Like lead. Lead is pretty dense. Several centimeters of lead or concrete. My couple sheets of paper that I was holding up in front of me a second ago are going to shield me perfectly from alpha particles, but not in the slightest from gamma rays. Beta particles, they're kind of in between. Beta plus or beta minus, they're in the middle. Medium penetrating power. Maybe a centimeter or two of flesh. So I'd prefer you didn't shoot me with a beta gun, because it'll go into my tissue. It's not nearly as bad as gamma rays, but a couple sheets of paper isn't going to protect me from beta particles either. On the flip side of this, though, look, the penetrating power of alpha particles is very, very low. But the ionizing potential, the potential to turn atoms into ions, is very high. So although they have a difficult time penetrating things, getting into things, if they get in, watch out. Because they can turn atoms into ions like that. Gamma particles, well, they have a very high penetrating power. I don't want to say they have a low ionizing potential, but they have the lowest of the three. So shoot me with the alpha particle gun, I'll shield it. Shoot me with a gamma ray gun, I can't shield it. But at least they don't do as much damage as the alpha particles do if they do get into my body. Beta, you could probably make a guess where that's going to be. It's beta particles are the fence sitters. They can't decide whether they want to ionize or not. They can't decide whether they want to penetrate matter or not. The beta particles are the fence sitters. They're always in the middle, whether we're talking about beta plus or beta minus. Let's do a couple multiple choice questions, guys. Just in the interest of time here, we won't bother submitting these ones. Take a look at 153. It's in the back of your worksheet booklet. This one says, when a neutral meson particle, what? A meson particle? Decays, it produces an electron in the process. In this process, it is most likely that what else is produced? Listen, guys. When in the last 20 minutes of talking about radioactivity or before the break, have we ever talked about a meson particle? Never. Never. So this is one of those ones that you got to think about a little bit. You don't really have to know what a meson particle is, okay, beyond what they tell us. And I can promise you, on your diploma exam, you'll probably encounter something like this. You see a term that you've never seen before. But I can also promise you that it'd be a question like this where it doesn't really matter what that is beyond the information that they give you. It's a neutral particle. The only thing they tell me about the meson particle is that it's neutral. So that's probably important. That's the only thing I know about this thing. It's neutral. And an electron, of course, is negative. So if neutral produces something that's negative, what else is going to be produced? Yeah, something that's positive, because we have to maintain neutral. It's kind of like the neutron changing into a proton and an electron, right? We have to keep the same charge. This has got to be something that's positive. So the answer is going to be D. Make sense? So we didn't need to know what a meson was after all, other than that it was neutrally charged, and they told us that, right? Don't panic when you see that, right? Okay, you're going to see that on an exam, terms that you've never seen before, but it's okay. Okay, it's not any harder than something like this. We don't have to know what it is other than the information they give us. Okay, let's take a look at another one here. A student obtains samples of pure quantities of two radioactive isotopes, X and Y, that contain equal numbers of atoms. You know what, actually, let's hold off on this one, actually, until we do the next topic, because we can answer part of this right now, but it's not going to make complete sense to us until after we've done the next topic. So let's skip that one for now. Okay, let's talk about this next topic, transmutation, which is obviously going to be a part of our radioactivity thing, our radioactivity discussion. Transmutation is the conversion of one element to another. Isn't that radioactivity? Isn't that the definition of radioactivity? No. Radioactivity is the spontaneous natural decay of an element. Transmutation is the conversion of element to another. In other words, transmutation is the result of radioactivity. This process of radioactivity happens where the nucleus decays. The result of this radioactivity process is transmutation. There's a conversion of one element to another. Transmutation can happen, among other ways, by radioactivity. Now, we're going to, for the rest of today, write what we call nuclear decay equations. They're similar to chemical equations in some ways, but different in some ways to chemical equations as well. I think you're going to find that they're pretty straightforward, though. A nuclear equation shows what we have before the transmutation and then what we have as a result of the transmutation. Kind of like a chemical equation shows what we have before the reaction and what we have after the reaction. But in a chemical equation, you always want to balance out the number of each type of atom, the number of carbons, the number of hydrogens, the number of oxygens, and so on either side of the reaction. With a nuclear equation, we're not balancing out the elements because the elements actually change. You can have carbon on one side and no carbons on the other side because carbons changes into nitrogen or something else. Rather, what we want to do with the transmutation, our nuclear equations, is balance out the protons and neutrons. In other words, the atomic numbers and the mass numbers. So we're not adding coefficients to make sure the carbons balance. We might add coefficients to make sure the number of protons balance. For example, this one that doesn't appear in your textbook says, write the nuclear equation for the transmutation of a radioactive isotope, radium-226. So 226 protons and neutrons, 88 protons undergoing alpha decay. Here's the way we're going to write this. We're going to start off, gentlemen, with writing this 226-88 radium on the left-hand side. That's what we start with. In chemistry, you might call that the reactant. In nuclear physics, we tend to call it the parent nucleus. You start with parents. What do you end up with after you have parents? Kids. Sons or daughters. The parent nucleus. What we start with. If you want to call it the reactant, go ahead, although that's really a chemistry term. It produces what? Well, it produces an alpha particle because it's alpha decay. So we've got a 4,2 alpha, or we've got a 4,2 He, whatever you want to write. Plus what else? Well, we don't need to make sure that we have the right number of radiums on the right-hand side. We need to make sure we have the right number of protons on the right side. We had 88 protons on the left side. We got to have 88 protons on the right side. 2 plus 86 gives me 88. We had 226 protons and neutrons on the left side. We have to have 226 protons and neutrons on the right side. So 4 plus what equals 226? 222. Now what is this? What element is this? Maria, what element is it? And how do you know? She's looking on a periodic table. The good news is these numbers on the bottom here are all in order. So if you're counting up 1 through 86, it's radon, yeah. Rn. So we start off with a nucleus of radium as it spontaneously, naturally decays by producing an alpha particle, this ionizing radiation, this alpha particle that can ionize atoms. It also produces as a byproduct radon. Now, the bad news is radon is radioactive as well. So we can have a nuclear decay chain. This radon can undergo another reaction, and its product may undergo another reaction, and so on and so on and so on and so on, until eventually, perhaps, it's stable. That may take 5 minutes, or it may take 5 billion years, depending upon how quickly these things decay. Does that make sense? I don't think that's crazy, eh? Okay, basically, you got to get the concept, but once you get the concept, you got to be able to add. And you get your calculators if you have a tough time adding 2 plus 86. Punch into your calculator. Okay, let's try this one. Let's say this should say beta negative decay, because there is beta positive as well, right? Beta negative decay. So write the nuclear equation for the transmutation of radioactive isotope lead-214 undergoing beta negative decay. Well, what do we start with? We start with what we got in the beginning here. Chemistry, we call it our reactant. In nuclear physics, we call it our parent nucleus. We get 214, 82 lead. By the way, if this number wasn't given to you there, that 82, how would you find out what it was? You look it up on your periodic table. You have to find that symbol, PB, somewhere on your periodic table, and then find 2 numbers on your periodic table. There's a big one and a small one. You're always looking for the small one. Okay, that big one for us in physics has no bearing whatsoever. We're not going to pay any attention to that big number. Always the small number, always the atomic number. So we got lead-214. $82 protons and a whole bunch of neutrons. It's undergoing beta decay, beta negative decay, so it's 0 minus 1 beta. Plus what? 0 plus what is 214? 214. So we had 214 protons and neutrons before. We still do. Maria, you had your hand up there, so I don't know if you had a question or an answer, but an answer. I got this feeling you have the right answer too, Maria. Minus 1 plus what is 82? 83. Well, that's a little bit odd. We had 82 protons, now we have 83 protons. Guys, remember what happened when we had beta decay? You had too many neutrons. So what did you do? We changed a neutron into a proton and an electron. So what happens? You got an extra proton now, right? Instead of 82 protons, you get 83 protons. 83 is bismuth you'd find on your periodic table. Now, I got bad news for you. In alpha decay, the alpha particles produce the daughter nucleus. Okay, that's the equivalent of the product in chemistry. The daughter nucleus is produced. That's it. In beta decay, You get this beta negative particle produced, you get this daughter nucleus, bismuth produced, but you also have this other thing produced. In 1930, a guy named Wolfgang Pauli predicted that there had to be something else because there was some missing energy. The energies just didn't quite match up. So he said, there's got to be another particle. He called it, in this case, an anti-neutrino. This anti-neutrino accounted for the missing energy. Now we have evidence to support this now, lots of evidence to prove that Wolfgang Pauli was correct. At the time, it was just it had to be, because the energy doesn't work out if this anti-neutrino doesn't exist. Now we know that he was right. In fact, we know that he was right in part, due to, in large part, to some work that's done in Canada, in Sudbury, Ontario. Anybody ever been to Sudbury, Ontario? You ever driven through Sudbury, Ontario? What's Sudbury famous for? They have nickel mines. You drive through Sudbury, Ontario, they have the world's largest nickel, like a Canadian nickel, as you drive into town. Drive across Canada, there's the world. I've thought about writing a book before, actually, about the world's largest things. Calling it the world's largest book. The world's largest nickel, the world's largest potato somewhere in New Brunswick, the world's largest Easter egg, Ukrainian Easter egg in Vegreville, and whatever. Anyways, they have the world's largest nickel in Sudbury, Ontario. And why do they have the world's largest nickel in Sudbury, Ontario? Because they mine nickel in Sudbury. And you mine nickel like way, way, way beneath the ground, like kilometers underground. For some abandoned mines in Sudbury, Ontario, they actually search for neutrinos. Neutrinos will penetrate. There's billions of neutrinos going through your body right now, and you'll never know it. It's fine. They're not going to hurt you. Okay? But you're not going to detect them because there's so much other stuff getting in the way of detecting them. When you're several kilometers underground, there isn't much there to get in the way. These neutrinos will penetrate the matter. They'll come from the sun. They'll penetrate the matter, go down into the ground, and we can detect them down there. And we don't have a whole bunch of other stuff that's kind of washing them out, right? Keeping them from being detected. So we've seen them, literally. We've seen these things in Sudbury, Ontario, these neutrinos that are produced as a result of beta negative decay. Okay? I got more bad news for you. If it's beta positive decay, it's not an anti-neutrino produced. If it was beta positive decay, you'd have what's called a neutrino produced. So beta negative, anti-neutrino, beta positive, neutrino. Let's try another one. We're going kind of reverse order this time. We're not told whether it's beta negative or beta positive or alpha or whatever. We're given the parent nucleus and the daughter nucleus here, right? And we got to figure out what it is that's produced. What kind of ionizing radiation that's made, alpha, beta, whatever. Phosphorus 30 goes to sulfur 30. 30 goes to 30 plus 0, right? 30 plus 0 is 30. 16 plus what is equal to 15? Be careful with the minuses and pluses, right? 16 plus what is equal to 15? Is it 1? It's minus 1. So what's that going to be? Call it a beta particle, call it an electron, doesn't really matter. Anything else? An anti-neutrino. Uranium-238 goes to thorium-234. Well, 234 plus 4 is equal to 238. 90 plus 2 equals 92. What's this one going to be? An alpha particle or a helium nucleus, right? Plus what else? Nothing. There's no neutrinos or anti-neutrinos produced here, right? This is a beta minus and beta plus. 13 plus 0 is equal to 13. 6 plus what is 7? Minus 1 or plus 1? Christian, minus 1 or plus 1 here? Plus 1. What's that going to be? Beta positive, right? It's a positron. or an anti-electron. Anything else? A neutrino, not an anti-neutrino, right? Neutrino. Somebody said to me one time, Mr. Dickie, how do we remember the whole anti-neutrino, neutrino, which one goes with which? Like, I don't just remember it. But then somebody else pointed out to me, well, it's kind of like negative is anti. Like, negative kind of goes with anti, doesn't it? It's a coincidence, but it works for us to help us remember that. The positive particle goes with not the anti, just the neutrino. Good? Okay. Let's leave it there for today. Let me assign your homework here. Your homework will be worksheet number 24, please. Just a small correction here. For worksheet number 24, question number 9, it should look like this. It says 80, lead 80 on your sheet. It should be 82 plus whatever. All right? So make sure you make that change from atomic number 80 to atomic number 82. Those should go pretty quickly for you tonight, guys. Again, just pay really close attention to two things here. Number one, the positives and the negatives, the beta plus and beta minus. That's the single most common mistake that people will make, is mixing up the positives and negatives and positives. The second thing is, make sure you get the neutrinos and the anti-neutrinos, okay? That's it for today, guys. Have a good night. We'll see you tomorrow.